All right, good afternoon, everyone. Nice to see you all here. So today is our third lecture on propagation and scattering of light. And like I said, this lecture and all lectures from this moment will be given in English. So today is our third lecture, and we continue to explore different tools of electromagnetism that may make our life easier in certain situations. As always, let's begin by recapping the content of the previous lecture. So the last time we learned a couple of tools, such as the Green's tensor formalism, the equivalence principle, and the eigenmodes of closed electromagnetic structures. And at the end of the lecture, we saw how these two concepts combine when we try to expand the Green's tensor of a closed system in a series of its eigenmodes. And today we're going to continue exploring such tools. We're going to learn a few more very interesting tools that come in very handy in many situations. And after that, the next time we start exploring different solutions of Maxwell's equations. So today we're going to start with the Pointing Theorem, which expresses the conservation of electromagnetic energy. So how do you approach the Pointing Theorem? The Pointing Theorem is a direct consequence of Maxwell's equations. And to obtain Pointing Theorem, we're going to start with Maxwell's equations, and we're going to take this combination of electromagnetic fields, H dot curl of E minus E dot curl of H. And we have our curl Maxwell's equations, so we can multiply this guy by H, we can multiply this guy by E, and subtract one from another, and using this, we obtain this expression, this identity. So this is just the direct consequence of Maxwell's equations. There is nothing new, nothing that I have used from the outside the system. I'm working completely within Maxwell's equations at this point. So already here you can recognize certain items in this identity. You can recognize the Poynting vector, and you can recognize the Joule laws in this equation. But this is not quite clear at the moment. So now we want to relate this guy to something more intuitive, to some other concept in electromagnetics, which we have an intuitive understanding of. And to do that, we're gonna integrate this expression over some volume V, arbitrary volume that contains some sources, some charges, maybe small volume, large volume, doesn't matter. And we're gonna apply Gauss's theorem that is gonna help us to calculate this term, because you remember from Gauss's theorem, an volume integral of divergence of certain vector can be related to the surface integral of the same vector. All right, so if we apply Gauss's theorem, we end up with this. So this is our Joule loss, which we integrate over this volume V. And this you can recognize as the Poynting vector. Poynting vector integrated over the boundary of our volume V dV, which expresses the incoming or outgoing energy flux depending on the sign. But still we have this term whose physical meaning is not entirely clear. So we're going to have to rewrite this term a little bit. And the following couple steps are going to be a bit sketchy, and probably you have done the steps already in classical electromagnetics lectures, but let me just quickly go with you through these steps. So to transform this weird term, we expand it in the following way. Oops, there was supposed to be some animation. It wasn't supposed to come out at once, but whatever. So this is the initial term. Now we add these two guys here, this one, and we subtract them at the same time. Okay, so this is just the derivative, this plus this is the derivative of this expression, which you recognize as the electromagnetic energy density, which can be calculated this way in a transparent, non-absorbing medium. This is important because when the medium gets dispersive, absorbing, everything changes. But as long as the medium is transparent, doesn't have absorption, doesn't have dispersion, this is exactly the electromagnetic energy density, which was proven in the standard electromagnetics. I'm not gonna repeat this proof right now. And this is something else. I don't understand how it works. Right, so this is the energy density, and this is something else which, in the case of absorbing and dispersive medium, can be shown to express dissipation. But as long as we are working with transparent non-dispersive medium, this is 0, and as a result, the Poynting theorem transforms into this, where for a second we can forget about this guy, okay? And we have only these 3 terms. So we have the energy density, the Poynting vector, and Joule dissipation. And this is the fundamental classical formulation of the Poynting theorem for transparent media. So on the left-hand side, we have the electromagnetic energy density, we have the Poynting vector, which describes the energy flow. So if you have certain volume V and you have some electromagnetic energy U, then S describes how this energy is moving, okay, where this energy is going. And finally, this guy expresses the dissipation rate. We can rewrite this formulation of the Poynting theorem. This is the integral version of the Poynting theorem. We can rewrite it, we can get rid of these integrals, and we can recast it in the local form, which is very compact. So this is the local rate of the energy change. Then we have the outgoing flux, and this equals to minus Joule loss and minus dissipation, which is this guy. But like I said, we can forget about this term in non-dispersive media. And with this, we end up with a very compact and convenient formulation of the Poynting theorem. Okay? So this is the graphical representation of what I just described, and it is very important to understand how all these quantities that enter the Poynting theorem come into play and what they mean. So Poynting theorem is essentially, it essentially expresses the balance of electromagnetic energy, the energy balance in electromagnetism. We have certain volume V. Inside this volume, we have the electromagnetic energy that is contained within that volume. And there are only, if we don't have any absorbing medium, there are only 2 ways how this energy stored inside that volume can be changed. It is either through the incoming flux of the Poynting vector, which can increase energy stored in that volume, or through the outgoing flux of the Poynting vector, which can reduce the energy stored inside V. Or it is through Joule loss, which is the work done by the fields, electric field inside that volume on the electric current density J. And if you have absorbing media, you also have dissipation, which can also only reduce the electromagnetic energy density, the total electromagnetic energy inside that volume. So this in words, without any mathematical symbols, expresses how Poynting theorem works. Once again, electromagnetic energy inside the given volume can be changed by incoming or outgoing energy flux, by work done by the fields on the currents, and through dissipation of that fields in absorbing media. Okay? So we can inspect a few practically common cases of the Poynting theorem. And first such case is the absence of any media and sources. In the absence of sources, we don't have currents J, and the Poynting theorem can be written in the following compact way. So this way, the rate at which the energy changes, the electromagnetic energy changes locally, is only dependent on the divergence of the Poynting vector S. So divergence is a measure how much incoming or outgoing energy flux you have here locally at this point, not through the entire surface, through the entire boundary of your volume V, but locally at this point. So if whereas in the integral formulation, we have this guy, S times N TA, which we integrated over our boundary. If we are interested only in one little point, if we're interested in how fast the electromagnetic energy is changing here exactly, then we reduce this to the local form, and this gets transformed to divergence of S. Okay. Another practically common case is the stationary case, where the fields are monochromatic, and the electromagnetic energy density at every point is stationary. Therefore, this guy disappears, and this equation now expresses the energy balance. The incoming energy flux balances dissipation inside at a certain point inside a certain volume, is balanced by dissipation, by currents, and possibly dissipation of the medium. And we can provide very useful expression for these quantities in the monochromatic case. So if all the fields are monochromatic, if they oscillate with this monochromatic factor, electric field, magnetic fields, and the rest, the Poynting vector, the time average Poynting vector averaged over one period becomes this, where E and the H are not instantaneous field values, but they are complex amplitudes, okay? Then the electromagnetic energy density can be written in the following way. And here, epsilon and mu can be not only scalars, but they can also be tensors. If the medium is anisotropic, these guys can be tensors. And then this expression will give you the correctly calculated electromagnetic energy density in an anisotropic medium. And then we have monochromatic expression for dissipation, if it is present. And we have the monochromatic expression for the extinction rate by the currents. So this is how much work is done by the fields on the current, on the electric current density inside the volume V or locally. So this all is true for the case of non-dispersive and transparent media. But if the medium is dispersive, the situation changes, and we need to be able to calculate the energy density inside that medium somehow. And the derivations that we have done so far, they don't really apply here. So we need to correct our procedure somehow. And to do that, we begin with the same procedure. We take Maxwell's equations, we calculate this combination of electric and magnetic fields, and we obtain this expression, this identity, where we assume the absence of any sources. Okay, this is not going to be important in order to obtain the formula for the energy density. There are no sources, there are only media, dispersive media, and fields. And the expression for the Poynting vector remains valid. In the case of dispersive media, we have the divergence S, plus the very same expression that we had in the beginning, which we managed to reduce to the electromagnetic energy density. So now we need to reduce this expression to the electromagnetic energy once again, but in the case of dispersive media. This is going to be a bit more complicated. And the way we do this is the following. Why isn't it working? So what we're gonna do is that we're gonna consider a wave packet. Instead of an arbitrary monochromatic or time varying field, we're gonna consider and narrowband wave packet, which describes a slowly varying electromagnetic field, slowly varying in time. This is going to be described by this amplitude in the Fourier space, which is going to be narrowband. And narrowband amplitude with a certain Fourier amplitude with a narrowband spectrum is going to give you a very, very slowly varying pulse of electromagnetic field. Okay, and in a similar way, we can calculate the time derivative of D by remembering how time derivative works in the case of Fourier representation. And we can write analogous expressions for H and for dB over dt. Okay, now we're gonna have to calculate this product and add the two terms together. Again, this is the electric field and the time derivative. And now we assume that the fields are varying slowly. They're described by some narrowband pulses. And after simple algebra, we find that period average value of this guy, of this product, equals this. I'm not going to go into the entire derivation of this. This can be found in classical textbooks in Jackson and in Landau. And combining this with analogous formula for the magnetic field, we will obtain the famous Brillouin formula, which describes the electromagnetic energy density in a weakly dispersive medium with possibly some dissipation. So this is a very important result in electromagnetism, because apart from providing a corrected result that can describe electromagnetic energy, for example, in metals, if you were to use the classical formula in which the electromagnetic energy is epsilon E squared plus mu H squared by over 4, you would obtain probably an incorrect result. You would obtain a negative permittivity, a negative energy density if you were to use this formula to calculate energy in a metal. Because remember, last time we talked about different models of permittivities. And you should remember that permittivity of any metal can be described by Drude model, which features negative permittivity below plasma frequency. And if you were to substitute this epsilon with Drude model, you would likely end up with negative energy density, which is of course unphysical. So this tells us that something needs to be done. The expression for the energy density needs to be corrected. And this is how we correct the energy density. But also it provides some interesting criteria for permittivities, for dispersive permittivities and permeabilities, because we know that, well, in weakly dispersive media, the electromagnetic energy is probably has to be positive. So these two guys, they need to be positive. If you want to check whether certain permittivity or permeability, for example, some model that you obtain from analytical derivations or from experiment is physical or not, you can check if these two criterions hold. If real part, derivative of real part of omega epsilon over d omega greater than 0, and if the same is true for me. Of course, this should not only away from the resonances, because close to the resonances, the media aren't weakly dispersive, they are strongly dispersive. And the whole game completely changes, and in fact, we can't even talk about any rigorous definition of electromagnetic energy, because I think Landau writes in 8th volume that in the case of highly dispersive and a highly absorbent medium, it is not possible to provide an unambiguous distinction between the energy of the field and energy of the medium. So this is much more complicated. But in the case of weakly dispersive medium, you can use this corrected Brillouin formula as a guideline, as a criterion for physicality of your permittivity and permeability model. So dispersive medium is any medium where permittivity or permeability is changing with frequency, where it is not essentially constant. Well, Yeah, that's a good question. Well, far away from resonance. That's also how far. What you could say that the criterion of weakly dispersive is that we are far away from a resonance. But what is the measure of being far from a resonance or close to resonance, right? So I think that I don't have a good answer right now. This is not something frequently discussed even in textbooks. So I think I would have to search for an answer to this question. That's a good question, but I can't answer it right now. So that's the Pointing Theorem for you. Now we're going to talk about a different symmetry of Maxwell equations that often becomes very convenient, and that is the time reversal symmetry. Let's say we have some process psi, I know, let's say psi, that is a function of time, and that satisfies certain equations of motion. It can be electromagnetic field that satisfies Maxwell equations. It can be a mechanical oscillator that satisfies the oscillator equation. It can be anything else. It can be the stock market, anything else, some dynamical process of time. Let's say continuous process of time. And now we're gonna introduce an operator, t, this curly t, that flips the direction of time, that maps t onto minus t. And that transforms the process psi in the following way. So every process psi, it maps into this guy psi as a function of minus t, which we're gonna call psi prime. This is just another process which can be expressed through the original process. Okay, these are just two different processes, psi and psi prime. And now we're gonna ask, does this new process satisfy the same equations of motion that psi does? And if it does, if psi prime, which is just psi as a function of minus t, is a solution to the very same equations of motion, then we say that the system obeys the time reversal symmetry. The system is time reversal. And we can visualize it graphically in the following way. We have the time, and we have some scalar process which is measured on the y-axis. Let's say it's real valued for simplicity. And we have the time that flows in the positive direction, and we have some process psi, the original process psi, which we call the direct process. And then we can map time backwards, and this should be directed this way. And we can consider the psi prime, which goes from here to here in the negative direction of time. And this is the reverse process. And if the system is time reversal symmetric, then this process is also a solution to the same equation. But if it's not, and if we start, for example, from the same point, or we start from here, then this process is not a solution. And if you flip the time, we're going to obtain a completely different process, which is not a mirror version of the direct process. The time, this system is not time reversal symmetric. So how does this all apply to electromagnetism? Well, in electromagnetism, what plays the role of this process psi? It's electric and magnetic field E and H. This is the pair of vector fields E and H that plays the role of this dynamic process psi. And so in this time reversal process, E is mapped into E minus t, but magnetic field is not, because remember, magnetic field is a pseudo vector. It's not just a real vector, it's a pseudo vector because it behaves in a weird way when you flip coordinates, and the same happens when we flip the direction of time. And this can be understood from the microscopic perspective. You see, magnetic field is created by the motion of charges. And what happens when we flip the direction of time? What happens to the motion of these charges? They start to move in the opposite direction. And the magnetic field being created by the motion of charges, not by charges, but the motion, is also getting flipped. This is, of course, very hand-waving argument, but one can understand this pseudo-vector nature of the magnetic fields in the following way. And this all leads to the following parity rules that electric and magnetic fields needs to satisfy when we want to flip the direction of time. So the electric field is mapped into E minus t, and we say that the electric field is even under the process of time reversal, but the magnetic field is mapped onto minus h of minus t, and we say that the magnetic field is odd under the process of time reversal. So how does this work? How does this operation work with the monochromatic fields in the Fourier space if we're dealing with monochromatic fields? Well, let's express time-dependent fields E and H via their Fourier components E tilde, H tilde, and apply time reversal to this and to this. And what we're going to find is that time reversal from E equals time reversal of this. Then we flip the time reversal and the integral operation, and we act with time reversal on this, which gives us this, which in turn gives us this. So in the Fourier space, time reversal of a monochromatic Fourier components of the field is the same components but complex conjugate. And in a similar way, it works with magnetic fields. And we obtain the following rules that describe how electromagnetic fields are transformed in the Fourier space when we apply the time reversal operator to this Fourier component. Okay. So do Maxwell's equations, are Maxwell's equations time symmetric? Do they satisfy time reversal symmetry? Well, it turns out that in vacuum, in free space, they are time symmetric, and one can easily change it by plugging this time reversed fields into Maxwell's equations and checking if they indeed satisfy the same equations. It is a very simple exercise. But does this property remain valid in the presence of media? It turns out that it doesn't always remain valid, and it essentially depends on the constitutive relations. It depends on the permittivity and permeability of your media. So it turns out that the criterion for a system to be time reversal symmetric is the following. Permittivity and permeability tensors must be Hermitian operators. In addition, if we have magnetoelectric coupling, remember that sometimes electric polarization is related to magnetic H field, and magnetization M is related to the electric field E, which sometimes does occur in nature. And in this case, the criterion of time reversal symmetry must be complemented by the third condition, which involves tensors Xi and Zeta that establish the magnetoelectric coupling between electric and magnetic fields. So what it means in the case of simple isotropic media, if we're dealing with isotropic media, that means that E, epsilon, and mu must be real, right? If you don't have any off-diagonal components, if these tensors are diagonal, they must be real. This means that Maxwell's equations are time reversal symmetric if and only if all the permittivities and permeabilities involved in the problem are real valued. And we know that from Pointing Theorem, for example, that real valued permittivity and permeability means there is no dissipation in the medium. there is no dissipation, probably there is no dispersion, and the Maxwell's equations become time reversal symmetric. As soon as you have any loss or gain in the system, or any combination of gain and loss, that violates time reversal symmetry. The system is not time reversal symmetric any longer. If you have loss, gain, or you have both, for example, you might have loss in one part of the system and you have gain in the other part of the system, and maybe they are equal in magnitude but opposite in sign. And sometimes it is tempting to say that, well, okay, maybe this system is time symmetric, but it is not. It will have, in many cases, very exotic properties, which we're going to study in the next term, so-called PT symmetry. But from the overall perspective, the system is not time reversal symmetric as soon as you have any dissipation or any gain present in the system. That violates time reversal symmetry. So now we're gonna look at a different, sometimes even more powerful property of Maxwell's equations, which is that of reciprocity. So reciprocity isn't exactly a symmetry of Maxwell's equations. It does not correspond to any integral of motion, but it is a property of solutions that Maxwell's equations satisfy as long as the media involved in the system satisfy certain very generic constraints which we very often have in practice. So let's say that we're dealing with a stationary system that is not changing in time. The fields may change in time, but the system, its permittivity and permeability do not change in time. The system is also linear, and the permittivity and permeability tensors satisfy the so-called Onsager-Casimir criterion, which says that the permittivity and permeability tensors are symmetric. Not Hermitian, as we had in the case of time reversal symmetry, but symmetric. Okay, so this allows us to say that these two identities hold. Essentially, we can multiply permittivity tensor by the electric field on the right or on the left, and the same is true for the permeability tensor. This is just a technical part which will help us to derive the property of reciprocity. Okay, so now how do we obtain actually reciprocity and the key identity that expresses the reciprocity? Well, it is very similar to how we obtain the Pointing theorem. Now we're going to calculate the following quantity using Maxwell's equations. Let's say we have two arbitrary systems of currents. We have J1, and in a completely different space, in a completely different universe, we have J2, which is a completely separate system of electric current densities. And this guy produces fields E1, H1, and this guy produces fields E2, H2. But the system is the same. The structure, the environment is the same. I'm going to try to replicate whatever I draw here on this side of the universe. So this is some epsilon mu, and these are the very same epsilon mu. So we have the same structure, but first we place some currents in the structure, and then we place a different distribution of currents to the same structure. And now we calculate this combination. We calculate the divergence of this difference of these vector products, where E1, E2, H1, H2 are these fields produced by the currents. And we apply Maxwell's equations because we cannot apply anything else. We don't have anything else. Well, we also apply this identity. And if we perform this calculation, and then if we also surround the entire volume by perfect boundaries, so you have electric conductor here, which means that electric field times n is 0 on the boundary, so we have perfect boundaries. And if we integrate that over volume V, we're going to obtain this, the surface term from this difference of cross products, and the volume integral, which involves our currents J1, J2, and electric fields E1 and E2. Well, still quite cumbersome, right? What can we do with this? Well, we can use the fact that our volume is surrounded by a perfect conductor, and that means that at the boundaries this guy is 0, tangential component of electric field is 0, and then this expression reduces to this, where the integration is performed over the entire volume. And now we are very close to the final version of the reciprocity. This already expresses the reciprocity in a way, but now we can simplify it even further, which is going to be even more useful for practical purposes. Now we're going to assume that J1 and J2 are point current densities, that they are localized at certain points. So this is some J1, and this is J2. Localized at certain points R1 and R2. They don't have to be the same, they can be different, and they can be located at different points, but they are point current. And if we perform the integration from these point currents, we obtain the reciprocity, the Rayleigh-Carson formulation of the reciprocity theorem, which is very, very important in electromagnetic. Yeah, here it is. So this is the Rayleigh-Carson way of expressing the reciprocity. Now J1 and J2 are 2-point sources, and E1 and E2 is their fields produced by, this is the field produced by the second current at the position of the first current. And here vice versa, this is current 2 multiplied by the field, electric field produced by the first current at the position of the second current. Okay, this might sound confusing, but whenever you look at the expression, you should immediately understand how it works. So there is a simple graphical way to visualize this relationship, this reciprocity property, and it is this. So we have the same structure in both cases, okay, but we have two different current densities and different fields produced by this current. We have J1 and we have J2, and if we calculate these quantities on the left-hand side and on the right-hand side, they must be equal as long as the system is reciprocal, which implies, remember, three things. Stationarity, the system is stationary. It is not changing, it is not modulated in any possible way. It is just God-given, it's not changing. Linearity, there is no nonlinear conversion effects, there is no current nonlinearity, no nothing. Electromagnetism is linear. And Casimir and Sager relationships, in other words, the tensors epsilon and mu are symmetric. As long as these three conditions are satisfied in your system, you are guaranteed to have this. And this becomes very useful and very important in many different situations. For example, when you have the problem of propagation through certain system and you want to know how electromagnetic fields propagate from side A to side B, from side B to side A, etc. And often this allows you to express, knowing how fields propagate from one side to another, it allows you to in some way understand how fields will propagate in the opposite direction. So loosely speaking, very loosely speaking, okay, the reciprocity says that exchanging the source and the detector. Let's say here you have the source and here you have the detector, and you measure how effectively the field of this field is projected into the detector. And here you replace their positions, you flip their positions. You have the source here and the detector here. And reciprocity says that by flipping the source and the detector, the ratio of amplitudes doesn't change. I can rewrite it. If I neglect the vector nature of this expression, I can rewrite it in the following way. E1 over J1 equals E2 over over G2. Okay, so this expresses, if this is our detector, this is what we have at the detector position here. And this is our source. And this is the ratio of the amplitudes. And this is the ratio of the amplitudes for the second situation. And the ratio of these amplitudes is equal due to reciprocity. Remember, this is a very loose formulation of reciprocity because here I essentially neglected the vector nature of the fields and the currents. But this gives you an overall idea what it means for a system to be reciprocal. So it is very important to emphasize the similarities and the differences between time reversal symmetry on the one side and reciprocity on the other side, because in the literature they are often confused, unfortunately, but they are not synonyms, they are different things. So if a system is time symmetric, it is necessarily reciprocal. So time reversal symmetry provides a sufficient condition for reciprocity. Any time reversal symmetric is necessarily reciprocal. But the opposite is not true. Time reversal symmetry is not a prerequisite for reciprocity. For example, consider a medium that is stationary, that is linear, and let's say permittivity and permeability tensors are symmetric, but the medium contains dissipation, and that violates the Hermicity criterions that dictate the time reversal symmetry. The system remains reciprocal, it is fully reciprocal, but the time reversal symmetry is broken by dissipation. So it is very easy to have reciprocity, but not have time reversal symmetry at the same time. This is a very common situation. So the system, any dissipation, any gain fully preserve reciprocity, and you can use the reciprocity formulation in order to solve electromagnetic problem, but it does violate time reversal symmetry despite reciprocity is preserved. Okay? And now we're gonna learn two different tools, two different symmetries that in some situations make our life very simple, in addition to Pointing Theorem and reciprocity that we just addressed. And the first such property is the scale invariance. Let's say we have certain system with certain permittivity, permeability, and E is a solution of that system of the monochromatic Helmholtz equation at some frequency omega. Some frequency omega. So this solution is, this equation is satisfied with our field E. Now let's consider the scaled potentials, the scaled permittivity and permeability. Well, we scale the distribution of permittivity and permeability space by factor alpha in the following simple way. So epsilon with index alpha is just epsilon as a function of alpha r, and the same for mu. So this is just scaling, okay? And if alpha is positive, let's say alpha is 2, tell me what it means for epsilon and mu. Is it going to be stretched or shrinked? Shrinked, of course, because this is larger than 0, and the scaled potential varies faster in space, twice as fast. So this is shrink, and if alpha is less than 1, this is stretched. Okay, now I'm gonna say that I'm gonna claim that we can show that the scaled version of the same field distribution, we can obtain a solution to the system by scaling up or down the same field distribution by the same factor. So how I'm going to obtain this new field distribution? Why? Well, by scaling it by the same factor alpha, stretching or shrinking in space, and at the same time by changing the frequency of that monochromatic stationary field by the factor alpha. so we're gonna, yeah, so if alpha is positive, that shrinks the field, that increases the frequency, and that decreases the wavelength. That makes sense, right? We increase the frequency, wavelength becomes shorter, frequency becomes larger. So let us prove this together. Let's say that, let's calculate the Helmholtz equation, the Helmholtz operator with new scaled permittivity and permeability, and the new scaled frequency acting on the new scaled field E. So this is rotor of rotor acting on the new field, and this is the new potential acting on the new field. So what are we going to do with this? Well, this is very simple. We just take alpha and place it here, and this part is a bit tricky. But what we need to do is that we need to calculate these rotors, which are linear operators. But we, instead of differentiating over R, over the old Cartesian coordinates, we're going to differentiate over the new coordinates, the scaled coordinates. And doing this allows us to have this prefactor alpha squared here. So now these two things, this and this, they share the common factor alpha squared, which we can take here before brackets, and in the brackets we're going to have this. We're going to have rotor times rotor with respect to some new coordinate, which we're going to call U. U is going to be our new scaled coordinates, stretched or shrink coordinate, and the permittivity times permeability as a function of the same coordinate. So we can write U here, we can write U here, and now this and this is just the same with only difference. I have R here, but here I have U, which is just a change of coordinates, change of notation. This essentially is the same as this, which means if this is the solution, then yeah, we know that E is a solution of Helmholtz equation at a frequency omega. So of course this equals 0, and this proves that the new scaled field, which is shrinked or stretched, is also going to be solution at the new frequency. And I think I forgot omega squared here, right? So this is going to be right, and here it's omega squared, c squared. Okay, and this is a simple graphical way to visualize this scale invariance. Here we have alpha, which is less than 1. That corresponds to stretched solution. So we stretch the space, we stretch the wavelength of our fields, and we decrease the frequency by the same factor, and the new field, the scaled field alpha, becomes the solution of the Helmholtz equation with the new permittivity and permeability for the new structure at the new frequency. And lastly, we're going to talk about another equivalence principle of symmetry, if you will, which is called the duality of electromagnetic equations. Again, let us consider a pair of vectors E and H, electromagnetic fields, which satisfy Maxwell's equations at a certain frequency. Let's say monochromatic fields that satisfy Maxwell's equations. And I want to make the following transformation to this pair of vectors. I want to rotate them by an angle theta in the following way. So what do I mean by rotation of these vectors? I mean this. I'm going to multiply H by the vacuum impedance, and by the way, vacuum impedance is square root so that these two things have the same dimension. And I'm going to multiply it. I'm going to act on this pair of vectors by the following operator, which resembles the usual rotation operator, except that I have unity tensors, unity matrices here in each cell of this matrix. So this becomes a super operator, which is a 2x2 matrix, and each element of this matrix is itself a 3x3 diagonal matrix, because each element acts on a vector. So these four guys need to be vectors. And this is just simple rotation, but not rotation of a two-dimensional plane, but rotation of two vectors. And so each vector gets rotated by this angle theta. And it is very easy to verify that this new solution rotated by an angle theta in this generalized six-dimensional space is also a solution to the same equations, to the same Maxwell's equations at the same frequency. This, in a way, highlights the symmetry, the equivalence between that's electric and magnetic fields have in electromagnetism. In a way, they are interchangeable as long as they are connected by this generalized rotation operation. And in the particular case, when this angle is plus minus pi over 2, this operation is called the duality transformation. And by plugging the angle plus minus pi over 2 in this operation, in this operator, we can see that this rotation corresponds to flipping electric and magnetic fields with plus or minus sign. So either E is replaced by H and H is replaced by minus E, or vice versa. E is replaced by minus H is replaced by E. And in this particular case of rotation by plus minus pi over 2, this is called the duality transformation. So electric field replaces magnetic field replaces electric field with an appropriate sign change. And this transformation in a very strong and simple way highlights the underlying fundamental symmetry that electric and magnetic fields have in electromagnetism. So this works only in free space without sources. Okay, and presence of media or sources generally violates duality and violates any kind of this transfer of this generalized rotation. However, in certain cases, we can restore this symmetry if we simultaneously apply certain transformation to the media. Let's say we don't have sources, we don't have currents, but we do have certain media that are characterized by permittivity epsilon and permeability mu. So it turns out that we can restore the duality transformation, which is this generalized rotation by plus minus pi over 2, if at the same time we replace permittivity with permeability and permeability with permittivity at the same time. No, and I want to emphasize that there is no minus sign here. We just flip them. And that preserves the symmetry, and it can be visualized in a graphical way, in a simple graphical way. So we have the old system where we have certain epsilon, certain mu, we have electric and magnetic fields, then we replace epsilon with mu, mu with epsilon, and at the same time we replace electric field to magnetic, magnetic to electric, and the new field distribution remains a proper valid solution of Maxwell's equations with the new potential. And by potential, I'm referring to the entire spatial dependent combination of all permittivities and permeabilities. Okay, I think that is all for today. As always, the key take-home messages from today's lecture is the Pointing Theorem and the conservation of energy in electromagnetism, the time reversal symmetry in electromagnetism, the concept of reciprocity, and the criteria of reciprocity, the relationship between reciprocity and time reversal symmetry, the scaling principle in electromagnetism, and the duality transformation. That finalizes the set of tools that we have to learn in order to be able to solve other real problems. And next week, we're gonna start looking at different regimes of electromagnetic propagation, and we're gonna start, of course, with the most simple problem of plane waves in a homogeneous medium, and slowly make our way to more complicated scenarios of focused beams, of spherical harmonics, of refraction, reflection, layered media, and so on and so forth. But for now, that's it. Thank you and see you next time.